In this problem, we are looking at three single-phase transformers. Each individual rating is 5 kVA with voltages at 200 volts primary and 100 volts secondary at 50 hertz. If we connect the high voltage sides in star and the low voltage sides in delta, in this problem, then we are to find what the line-to-line three-phase voltage that should be applied in order to maintain the rated winding voltages. Also, we have to calculate and show the line and phase current magnitudes in both the low voltage and high voltage sides corresponding to the rated conditions. Finally, we have to calculate the kVA flowing in the primary and secondary of the transformer at rated applied voltage. Here, the idea is not to exceed the voltage and current ratings of the high voltage and low voltage windings of each single-phase transformer. Now, for each transformer having a rating of 5 kVA, 200 primary volts and 100 secondary volts at 50 hertz, we have the rated voltage of each high voltage coil or winding is equal to 200 volts. The rating of each low voltage coil or winding is 100 volts. The winding turns ratio, we will call it A subscript PH for a single phase transformer, is equal to 200 divided by 100 or 2. The rated current of each high voltage coil is 5 kVA divided by 200, which equals 25 amps. The rated current for each low voltage coil is 5 kVA divided by 100, which equals 50 amps. In this case, the high voltage windings are connected in star and the low voltage sides are connected in delta as shown in this slide. Thus, the line-to-line voltage to be applied to the high voltage side must not exceed 200 times the square root of 3, which equals 346.4 volts. This will ensure that the rated voltage, 200 volts, is applied across each of the high voltage windings, and that 100 volts is induced in each of the low voltage windings. Obviously, the available line-to-line voltage on the low voltage side will be 100 volts, since the windings on this side are connected in delta. Now, the question is, how much line current should be allowed to be supplied by the low voltage side when balanced three-phase load is connected across it? The constraint is that we should not allow overloading of any of the coils in terms of current. Since rated current of each low voltage coil is 50 amps and the windings are connected in delta, so the corresponding line currents allowed on the low voltage side will be the square root of 3 times 50, which equals 86.6 amps. Note that the line current equals square root 3 times the phase current in a delta connection. But we know for any individual transformer, the low voltage coil carries a 50 amp current. The corresponding high voltage coil must carry a current of 50 divided by the turns ratio, or 25 amps. Thus, the high voltage side line current drawn from the supply must be also 25 amps, as these coils are connected in star. Note that the line current equals a phase current in a star connection. Now we are in a position to calculate the total kVA handled by the three-phase transformer bank. Referring to the low voltage side, the transformer supplies 86.6 amps line current at the line voltage of 100 volts. Therefore, the total kVA supplied is the square root of 3 times the line-to-line voltage times the line current, which equals square root of 3 times 100 times 86.6, and that is equal to 15 kVA. Similarly, the kVA drawn from the supply is square root of 3 times the voltage line to line times the line current, which equals the square root of 3 times 346.4 times 25, and that is equal to 15 kVA, which should not be a surprise, as the power going into an ideal transformer must equal the power coming out of an ideal transformer. Thus, we see the total kVA becomes 3 times the individual kVA rating of the transformers. Since the transformers are assumed to be ideal, the total kVA input should equal the total kVA output. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. Jackery Canada at this web address. Bluetti Canada at this web address. Bluetti USA at this web address. And Bluetti Australia at this web address. And finally, EcoFlow may be found at this web address. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.